Thank you. Oh, a little too soon. I want to thank everyone for coming to my talk, and I want to thank the organizers for allowing me the opportunity to speak in the World of Group Craft conference. And the name tickles my soul. So if at any point people have questions, shoot them in the chat or just interrupt. Okay, so today I'll be talking about quantifying conjugacy separability of lamplighter groups, and this is joint with our own Michal Ferov. And our motivation is to study infinite groups with finite groups. So there's this general philosophy that goes, oh, you have this hard thing, so let's jam it into small things which are easier to understand. So for the context of this talk, the hard things to understand are infinite groups, and the easier things to understand are finite groups, though that's kind of a lie because the classification finite simple groups exist, but let's not go into that. So for us, we're going to study groups with finite quotients, by their finite quotients. Okay, so what are some properties that we're interested in studying? Well, the focus or applications of a lot of results here are actually to decision problems. But there are other ways of applying this when it comes to topological models for your group or group theoretic models for a geometric space that you care about. So we have a classic question or classic problem, and that is the word problem. And I would imagine most of everyone knows this, but let's just remind ourselves what this is. So let G, this is a group, and we're going to equip it with a finite presentation. The question is the following: does there exist a finite time algorithm, okay, to determine whether a given word or finite word, so whether a finite word is trivial or not, or represents the trivial element? So this is known as the word problem. And the thing is that this is a well-studied subject in group theory, connection of logic and stuff like that. So the thing is that how can we use finite groups or finite quotients to solve the word problem? So how can we use finite groups? Or how can we use finite quotients to provide a solution? So for a solution to the word problem. So this definition was introduced by Maltzow, if I remember correctly, 1958. So a group G is residually finite. Now, our interest here is in finitely generated groups, but this actually definition can apply to any group. But for our purposes, just assume all of our groups are finitely generated. A finitely generated group is residually finite if, for all non-trivial elements, so for all G not equal to 1 in G, big G, we have a finite surjection onto a finite group. Oops. Not now. So in morphism, so phi from G to Q, we can just assume it's surjective, Q is finite, and phi of G is not trivial. Okay, so this here is also a well-studied subject, and there's lots of familiar classes of finitely generated groups that are residually finite. So free groups, something that everyone likes, something only I like, Nilpin groups. That's a joke, but yeah. Linear groups. And then, for instance, fundamental groups of closed three manifolds. So closed three manifolds. And then an example of a group that's not residually finite is the Bohm-Sartre group 2-3. Okay. So this actually solves our original question in the following way. I have a half hour, is that correct? Or 20 minutes?
25 minutes.
25 minutes? Okay, thanks. Residual finiteness actually gives us a solution. This is also in 1958. So if G is finitely presented and residually finite, then it has a solvable word problem. Okay. Now the thing is that once you have a collection of groups where you know this collection, every member of this collection of groups is residually finite, and let's assume your collection of groups is finitely presented, how can you use residual finiteness to actually distinguish our groups? So what we can do is we can now start asking, we can ask about the asymptotic behavior of our solution. So what I mean here is, for people who are familiar with this, you can ask like the runtime, the amount of space you need, and this is for like doing computations and stuff, so on and so forth. So since our focus or tool to study the word problem is finite groups or finite quotients, what we want to do is we want to quantify residual finiteness. So we're going to quantify residual finiteness. Okay, so we have a Fond definition. We're going to assume G is residually finite and it's a group. And we're going to let G, little g, be a non-trivial element. Then the depth function applied to this element, this is the minimum over all finite groups where there is a surjective homomorphism from G to Q, so that the surjective homomorphism sees G. So there are many ways to interpret this, but one way to look at this is it tells us how big of a group we need to see G. We need to witness or see G. Now, it's important to give credit. This was introduced by Bourabi in his paper in 2010. Okay. Now, we have a way to measure how hard it is to detect a single element with finite quotients. Now what we're going to do, this is also from Bourabi, is actually package this together into a function. So G is finitely generated with a finite generating set, S. And then the residual finiteness function with respect to S, this is the maximum over all elements of length less than n, and here G is not equal to 1 of the depth. Okay, so the interpretation of this is that this tells us the difficulty of seeing elements using finite quotients as we range over the, or as we vary over the n ball. Now, the thing is that this function, while it depends on the generating set, what this happens is that if you have two generating sets, S1 and S2, and they're both finite, then the asymptotic growth of the residual finiteness function, they're the same. So for instance, they would both grow like a polynomial to the kth power, maybe with different coefficients, but asymptotically they have the same behavior. So like a picture of this depth function is as follows. So the idea is, imagine this blob is your group G. You have your identity element here. Then the depth of G is small if we can find a large normal subgroup that doesn't contain our element G. And this corresponds to going to a small group here. And you have a similar picture for when depth of G is large. Okay, so this is the first instance where we're studying separability or decision problems using finite quotients. And it's for a problem that's well known, that's the word problem. And we do this using a well-known property, residual finiteness. So you can ask a similar question or ask for a similar story to this conjugacy problem. The idea here is that if G and H are in G, this is not quite right. Can we distinguish conjugacy classes in our group G using a finite time algorithm? Okay, so this is the conjugacy problem. And then we have a conjugacy variant of residual finiteness called conjugacy separability. And the idea here is that if I have two elements, G and H, in our group, and G is not conjugate to H, so if for all G and H that are non-conjugate, there exists surjective homomorphism to a finite group where phi of G is non-conjugate to phi of H. Okay, and then Malsoff also showed the following in the same paper, that if G is finitely presented, conjugacy separable, then G has a solvable conjugacy problem. Now, this is actually a generalization of residual finiteness, because if your conjugacy is separable, then all elements, central elements, are distinguished because they're conjugacy class, because they are their own conjugacy class. That includes the identity element, meaning that you can separate every element from the identity element using a finite quotient. Therefore, you're residually finite. So Lawton, Lauder, McReynolds in 2017, they are able to actually give a way to quantify residual finiteness. So given two non-conjugate elements, and assuming your group is conjugacy separable, we want to look at the minimum over all finite groups where Q finite, where there's a subjective homomorphism to our finite group Q, so that the two elements remain non-conjugate. So here what we say is that Q separates the conjugacy classes of G and H. And continuing this picture, we have our conjugacy separability function, which is well defined up to asymptotic growth, independent of generating set. What we do is we take the max over all elements, G and H, in the n ball. G is not conjugate to H of the conjugacy depth function. Okay, so this, what it will do is it quantifies the conjugacy problem or conjugacy separability, which quantifies the solution to the conjugacy problem with finite quotients. Okay. Now, this function here, the conj function, is less well studied. However, there have been a number of results that have been coming out in the past 4 years or so, describing the behavior of this conjugacy function, conjugacy separability for different classes of groups that are of classical interest. So, oh yeah, and the thing is, I didn't mention this earlier, but examples of CS groups or conjugacy separable groups, for instance, free groups, surface groups, polycyclic groups, and there's a bunch more. Non-example, a relatively simple example, is SL3Z. Okay, so can we understand asymptotics for the conjugacy problem or conjugacy separability, so for CS, for the above groups, classes of groups? Okay, so Louder, and McReynolds, they show the following: is if G is not a abelian free group or a surface group, then the conjugacy problem or the conjugacy separability has really horrible growth rate, asymptotic upper bound. So this is n to the n squared. So this is super factorial. Okay, and then no good lower bound has been provided. So the best lower bound I can think of right now is linear. So what we got is n is less than conj of g, which is less than n to the n squared. So basically, we have no idea how this function behaves at all. And then me with Jonas Dare, 2019, we show that if A is virtually abelian, and this isn't hard, but it's worth stating, then log n grows slower than conj of A, and this grows slower than log n to some power of d. Then this is P. And in the same paper, we show is that n virtually nilpotent not virtually abelian, then we have that n to the k1 grows slower than conj of n, and this grows slower than n to the k2, k1 less than k2, and these are integers, natural numbers. Okay, well, polycyclic groups are actually unknown right now. So if G is polycyclic, not virtually nilpotent, well, there are no good bounds for but I'm willing to make the following conjecture. In this case, the conjugacy of G, when G is polycyclic, not virtually nilpotent, should be exponential. And if you're interested in why, I can explain a little later. So this is all that is known. However, in forthcoming work, we look at other classes of solvable groups. In particular, we're going to look at the lamplighter group over P, or prime P, which is Z mod PZ wreath Z. We can actually show the following. P, Michal Ferov, and this hopefully comes out this year, but you know, there is a pandemic going on, so we'll see. The conjugacy of the lamplighter groups grows on the nose is 2 to the n. In fact, we can generalize this. There are two generalizations we can do. Okay. If A is finite abelian, then conj of the A wreath product of Z, this grows to the n. And the other direction we can generalize, generalization 1. And then for 2, if k is greater than 1, then 2 to the n goes slower than conj of A reads zk, which goes slower than 2 to the n to 2k. And it is 2:25, so that is all the time I have. Thank you.
Let's thank the speaker. Are there questions for Mark?
You mentioned that you had you had a reason for believing that the conj function for non-virtually nilpotent polycyclic groups is exponential.
Yeah, like what you want to think is this. It's heavily related to how the algebraic properties of a polycyclic group that's not virtually nilpotent. For instance, you can always realize them as, for instance, like an arithmetic lattice in a solvable algebraic group. And when your solvable algebraic group is not nilpotent, what will happen is it'll have this non-trivial maximal torus. And then this non-trivial maximal torus acts on the nilpotent part in a very convoluted way. In particular, what it does is it kind of glops together central elements in the nilpotent group that it's acting on. And then these central elements are actually very difficult to separate, because not only do you have to separate, you end up, instead of separating like these individual elements, you have to actually separate whole centralizers of these groups, of these elements, which is not the entire nilpotent group, entire polycyclic group, but it's still relatively large. So it's really following from the fact that like you have this linear algebraic group with a non-trivial maximal torus, and oftentimes this will be defined over a number field that will have index greater than 2, for instance. So like by the Dirichlet unit theorem, it will have like relatively big unit group for the ring of integers.
So is this known for any special cases like lattices in Sol? Is that?
For lattices in Sol, it is 2 to the n.
Oh, I see. Okay, thanks.
Any other questions?
Yeah, so I have a question. So do you know if there's a way to use these kind of ideas to work with the last decision problem, the isomorphism problem?
I have no clue. I actually haven't even seen anyone talk about that.
Okay, thank you.
I might know the partial answer to that.
I have a partial answer.
Probably not, because like there are examples of groups that have the same profinite profile, so like they have the same finite quotients, even though they're not isomorphic. And I think it might get even worse that these are groups that are not isomorphic, but their profinite completion is. I might, though my memory is a bit hazy on that, so.
But that's correct.
I don't really think, yeah. So, but I don't really think that it applies to isomorphism problem, because it's more like about recognizing specific subsets within your group.
Yeah, that's right. So, for instance, there is like a relatively new industry in profinite geometry of groups, that is profinite rigidity and absolute profinite rigidity. So the thing is that, as Michal was saying, if two groups have a same set of finite quotients, then we don't even know if they're necessarily isomorphic or not. In fact, it's a hard problem, and there's been some very, very powerful results where they show, well, certain groups, you can actually distinguish them by their finite quotients. But like, for instance, we don't know if there exists a group with, we don't know if there exists a group with the same finite quotients as the free group of rank 2. And then like, even if they have the same finite quotients, right? We don't necessarily know how these normal subgroups that correspond to these finite quotients sit as the lattice of subgroups within the ambient group. So there's a lot not known here, and even when there's stuff known, there's still like additional properties that you have to take into account if you would want to use this to understand isomorphism classes of groups.
All right, so I'm going to cut things off here because it's time for the next talk, but I'm going to suggest if there are further questions that they be moved to the Discord at this point. Thanks, Mark. Let's thank Mark again.
Thank you. Yeah, I'll just put my email into the chat if you have more questions.
Thanks, Mark. That was great.
Okay, everyone, I have a lot to do today, otherwise I would stick around, so. All right, everyone have a good rest of the conference, I guess. Bye.
Hi, Jesus. I've made you co-host, so you should be able to share your screen if you want to try that out.